You spent many years in fluid mechanics.
Yes.
How do you think the field has changed during the time since trying to program something to look at convective flows to now?
There's been no revolution in the sense that the computing has become much more sophisticated, the method more sophisticated, turbulence still unsolved. The numerical methods change a lot. If you look at what our colleague Peyer does, it's way above what I was doing when I last did that. But I guess the main problem is still unsolved. The people in the field have changed attitudes. It used to be so that the fluid mechanics, that it was easier to publish a numerical method in the paper in the mathematical literature, but not in the fluid mechanics literature. They felt that this numerics was not respectable or not accurate enough, not reliable. And that attitude has to a large extent changed, as it must, because that's, of course, the way to do things. But there's been a fast and thorough improvement of methods, but not really a revolution in the problem which is most interesting, which is turbulence.
Is turbulence solvable?
Well, I'm sure it is, but the question is how. And what's missing is some fundamental new idea. It's a mix of uncertainty, structure, and lack of structure. And at this point, you can deal very nicely with a system which is very random, like a perfect gas in equilibrium, or a system which is deterministic. But the mixture is not, you don't know what to do.
Well, I should probably be more careful about the word solvable, because I don't know what that means. But I would say...
computable from first principles.
You think it is?
I think it is, but you need some new idea, which we don't have. So at this point, people try eating at the edges of the problem, but it's not making enough progress.
Is there such a thing as a problem that's just probably too hard? Too many scales involved, too many things involved?
No. There are problems that are too hard now, but not... Okay. My feeling is that anything which once you understand it, you can do it. And the understanding, the calculations progress together, but you need some new idea. Chaos was a new idea. Chaos explained how come you can have a random phenomenon in deterministic equations, and therefore it provided an insight. But it has not helped solve the problem, because what you can describe well by chaotic dynamics and turbulence is still laminar. Turbulence is much more complicated. So, but that was a new idea. One needs some other new idea which will actually allow you to go into the turbulent regime, and it's not there yet.
Do you think that new idea will come from mathematics or statistics, or what has to come into play?
Well, the problem of turbulence is a mathematics problem, because the equations have been known for a century and a half. Navier-Stokes equation. No one has any doubt about their validity. There can be no doubt about their validity. So the problem is solving them. And so you need to solve them, you need some good representation for the solution, some good candidates, some insight, and it's not there. But other fields in which the issue is mathematical, that you know something about the equations and the roadblock is being able to solve them. Many problems of quantum field theory, you could compute well enough. Extracts information from the theories to compare with experiment, for example. But so it's mathematical problems. And math develops, as you know.